In this censored reliability test, notice that the test stops as soon as a predetermined number of samples fail. So in the earlier example taken from Gnedenko's book, we stopped at a fixed time, regardless of the number of failures. Now we are stopping as soon as 3 failures occur. So in general, are failures. And we record the individual failure times. We need to estimate the mean time to failure. And as before, we know that the distribution of time to failure for the item is exponential in nature. So let's set the problem up carefully. So we start with n samples, each with time to failure xi. The xi are IID, independent and identically distributed exponential random variables with the same parameter lambda. So I goes from 1 to n. All these n samples are put to test at time t equals 0, and our items fail at times tau 1, tau 2 up to tau r. So these are the instances that we record, and then we stop the test. So we need to estimate the mean time to failure. Obviously, if we just take the mean of these 3 numbers, 144, 182 and 243, it would be overly pessimistic. We understand that, because it's only those 3 that failed and 6 of them did not fail. So we need to somehow take those into account. So one way to proceed would be to define the distribution of successive times to failure. So the time to the first failure, the time to the second failure, and so on up to the time to failure number r. And we have looked at this sort of problem before when we looked at the Poisson process and the sum of individual exponentials leading to shock number k and gamma distribution for the time to kth shock, and etc. So this will be a similar setup, but let's proceed step by step. So let delta t1 be the time to the first failure. So how do we derive the distribution for this delta t1, this random time to first failure? Turns out that we'll make use of the fact that all the x's are IID exponentials. So we don't find the CDF, but we start with the complementary function, the reliability function, if you will, and we are trying to find the probability here that the first time to failure, the time to the first failure is greater than some constant tau 1. So that actually gives us a very quick answer. It basically states that no item fails before tau 1. We are starting from 0. First failure doesn't occur up to tau 1. So that's what we are asking. And so that basically means, in terms of all the x's, is x1 greater than tau 1, x2 greater than tau 1, and all of them greater than tau 1. And because they are independent, we can multiply the probabilities. And because they're exponential, the product of all these exponential functions turns out to be exponential of minus n lambda tau 1, because lambda is constant for all of them, and which basically means if the complementary CDF of a random variable looks like this, exponential of minus a constant times the value of the random variable we looked at, it basically means that the random variable is exponential. So delta t1 is exponentially distributed with parameter n lambda. So that is very good to know. So then let us see if we can be more ambitious and try to find the distribution of the next time between failures. So delta t2. So we are not looking at time to failure, but time between failures. So the time delta T2 is the time that it takes for the second failure after the first one. So what is the distribution of this delta T2? Let us proceed similarly. So let's take the exceedance type event. So delta T2 greater than delta tau 2. So that's the probability which we are trying to find. Now that is, we have to be very careful in this definition. It's basically asking for the probability of an event which is no surviving item fails before tau 1 plus delta tau 2. That's very important. No surviving item fails before tau 1 plus delta tau 2. Because all these elements are starting service at t equals 0. Delta T2, the time between the second and the first failures, needs to be defined in terms of the x's. So that's how we are doing it. And that in terms of all the x's looks like this. So each xi is greater than the time to first failure plus delta tau 2. Okay, so that's clear, except we need to define that x subscript parenthesis 1. So x subscript parenthesis 1 is what you see on your screen. That is the time to the first failure. So the weakest element, if you will, the time that it failed. So the first element to fail is x subscript 1, and so it's time to failure. So this intersection event goes for all i's 1 to n except the index corresponding to the element that failed first. Now the surviving item. So this is not the end of it. This is conditioned on the event that all the elements except that x subscript parenthesis 1, they survived. So they are all greater than x subscript parenthesis 1. So they are all greater than the element that failed first. So with that, now we have an event like we have a probability of A given B. So now let us use that definition. So P of A given B is P of AB over PB. So that lets us just express the same probability in terms of a fraction. So now let us look at the numerator. The numerator, the intersection of those two events, just to clear that the one on the right is already contained in the one in the left. So the intersection of the two would be just the left one. So we can simplify the numerator as intersection of all the x's greater than the time to the first failure, the random time to the first failure, plus that delta tau 2 that we have that we started with, and in the denominator we have all the surviving elements greater than the time to the first failure. So that is the point at which we then bring in another conditioning. So let's move to the next slide. We have already found out that delta T1 is exponential with parameter n lambda, and now we are in the middle of finding the distribution for delta T2, the time between the second and the first failure, and we ended with a ratio of 2 probabilities. Now let us condition both the numerator and the denominator on the time to first failure. So x subscript parenthesis 1. So we are going to use the theorem of total probability on x 1, taking all possible values tau 1 integrated over the entire range. So we have done this sort of formulation before many times. So let's just do it rightly, step by step, and then once this is done, we can we can enter the density functions, the distribution of all the x's. So and we also use the fact that all the x's are independent and identically distributed. So given that x subscript parenthesis 1 is tau 1, that does not change the distribution of the individual x's, all the other x's. So we can invoke the exponential nature of all of them. There are n minus 1 of them, so we multiply all of them in the numerator and also in the denominator. Once we do that, we can factor out the term that is independent of tau 1, so we bring it out of the integration in the numerator, and what we end up with are two common factors in the numerator and the denominator, and they cancel out each other, and what we are left with is a simple expression of exponential of negative a constant times delta tau 2, which is what we started with. So as soon as a random variable has a complementary CDF looking like that, it must be an exponential random variable. So just like delta t1, delta t2 is also an exponential random variable with parameter n minus 1 lambda. Delta t1 had parameter n lambda, delta t2 has parameter n minus 1 lambda.